we will talk a little bit about what happens when you have a rigid object that actually isn't rigid and it can be deformed in some way. And in those cases, we can talk about something called stress and strain. So all materials, even though we've assumed that they are rigid objects that don't really change shape, they will change shape if enough force is applied to the object. So in reality, all objects are actually deformable to some extent. And so the shape can change in a number of ways. We could lengthen it, we could change the entire volume, we could actually just change its shape in terms of deforming it in some way that's not just its length. But basically what happens is that there are internal forces inside the object that resist this deformation. So we define something called stress and strain. So stress is basically a quantity that is directly proportional to the force that's actually causing the deformation. And in general, the stress is that force per unit cross-sectional area. And so we'll talk a little bit about how those differ depending on the type of stress that's actually being applied. But in general, stress is related to the force and then the cross-sectional area where that force is being applied. The strain, on the other hand, is basically measuring how much deformation actually occurs. So how much did the length change compared to the original length? How much did the volume change compared to the original volume? And so for sufficiently small amounts of stress, the stress is proportional to the strain. So the amount of force per unit area that you apply is directly proportional essentially to how much the object is deformed. But you can reach a limit where you can't go back and you basically, they're no longer proportional to one another. So we call this proportionality constant the elastic modules. So the elastic modulus is defined as the stress per unit strain, and this is for all solid objects. And so we have three different types of modules. You have Young's module, which measures the resistance of an object, a solid object, to change in its length. We have the shear modulus that measures the resistance to motion of the plane within a solid parallel to each other. So we'll see a picture of that. So basically, when you shear something, you're kind of applying a force maybe to the top of it, and because of friction, it might kind of bend in a certain way. And then we have the bulk modulus, which measures the resistance of a solid object or a liquid to their change in volume. So in this case, essentially you're applying a force on all sides of an object and it causes the object to change shape all the way around in terms of its volume. So here's a picture of what the Young's modulus, or the stress per unit strain, would look like for an object where the force is applied along the length of the object, and the object has some cross-sectional area. So this block right here is the cross-sectional area, and as a result of this force being applied, the object actually changes length compared to its original length. So if I removed the force, the object would basically go back to its original length. And so by definition, this is called the tensile stress over the tensile strain. And so Young's modulus will tell us something about the type of material that we're dealing with. So if this is made of aluminum, the amount of stress per unit strain is going to affect this differently versus if it was a piece of copper or a piece of plastic or something like that. So we define the tensile stress as that force that's being applied here per cross-sectional area. And the strain is the change in the length. How much did that length change compared to the original length? So as I mentioned earlier, the elastic behavior of an object is such that the stress, here's the stress along the vertical axis, and the strain are directly proportional to one another, and they behave in this elastic, it has this elastic behavior where they're proportional until you reach the elastic limit. And after you reach the elastic limit, then they're no longer proportional and they start to behave a little bit differently, and then you can reach a point where you're just applying so much force per unit area that the object would actually break. So we're looking at situations in this elastic region right here. Now, the shear modulus is a situation where the elasticity changes the shape of the object. So an easy example here is like if you put your textbook on on a table, and then you applied a force on the top, because of friction on the bottom, you've got sort of this equal and opposite force where the object doesn't actually move, but those two forces, which are separated by some height here, cause the object to shear. And basically what that means is that it changes the shape. So it's no longer like in this picture here, we had a sort of not a cube, but a rectangular like box or something like that. And so we've got a force on the top, a force on the bottom, and because of those two forces being separated from one another by this height here, h, we get this change in shape at the top that actually changes length and shears with respect to the bottom portion. So it turns out that in this particular case, the cross-sectional area is directly tied to where the force is being applied. So it's the top area here, and then the force is applied right along that area. And as a result, we get this delta x. And so by definition here, we have the stress, the shear stress per unit strain, and we have the shear module. And the shear module is going to depend on what this is made of. So if this is a book, it's going to have a shear module. If it's made of a piece of aluminum, it would have a different shear module. But in general, it's still force per unit area for stress. Force here is parallel to the area. And then the strain is the change in the length over, in this case, the height, which is the difference between those two, where those forces are applied. And then finally, we can have the bulk module. And in that case, basically you have force being applied on all sides. And as a result, there was some initial volume of this, but because force was applied on all sides, it decreased the volume. And so we have the bulk module, which is the volume stress over the volume strain. Stress is still force per unit area, except in this case, we've got forces on all sides and we've got all of these different areas. So it's kind of a little bit like Young's modulus in the sense that it's looking at the force per unit area and how it's causing it to either stretch or compress. But we just have force on all sides. And then we look at the strain as how did the volume change compared to the original volume. And so it turns out that force per unit area is defined as pressure, and it makes more sense to talk about how the pressure changed for the pressure on all sides of this box. So it might have started off with some initial pressure, like atmospheric pressures just sitting outside, and then you put it in underwater or something like that, and it causes the pressure to increase. And as a result, the force per unit area changes. And so the bulk module is the change in pressure, which is the stress over the strain, which measures how the volume changes compared to the initial volume. So there is a table that provides all of these elastic module values for different materials, and we have Young's module for many materials. We have the shear module, and then we have the bulk module as well. So we might have to refer to this table to tell us what those modules are based on the type of substance that we're dealing with. So we can look at an example. We have an example of a solid brass cylinder, a sphere. It's initially surrounded by air, and the air pressure exerted on it is atmospheric pressure, which is 1 × 10⁵ newtons per meter squared. The sphere is then lowered into the ocean to a depth where the pressure is very large, so 2 × 10⁷ newtons per meter squared. And we know the initial volume of the sphere in air was 0.5 meters cubed. And we want to know how much does this volume change once the sphere is actually submerged. So what do we know? Well, we know the initial pressure, and we know the final pressure, and we also know the initial volume. Our goal, of course, is to see how the volume changes, and we know that this is a solid and that there's pressure change. So we would have to use the fact that the bulk modulus, which measures the stress, change in pressure over the strain, change in volume over initial volume, and that will allow us to figure out how this volume here changes. So what else do we know? Well, we can determine the change in pressure, which is just this final pressure, 2 × 10⁷, minus the initial pressure, which is 1 × 10⁵, and I get a change in pressure of 1.99 × 10⁷ newtons meters squared. The other thing we know is that we have a solid brass sphere. And so if I went back a slide and I looked at that table, I could look up bulk module for the for brass, and I would get 6.1 times 10 to the 10 newtons per meter squared. So I can rearrange the expression for the stress per unit strain by multiplying the quantity on the bottom on both sides, and I get that the bulk modulus times the change in volume over the initial volume is equal to negative the change in pressure. And then I can plug in the values that I know. So I know the bulk module is 6.1 times 10 to the 10 newtons per meter squared. I'm looking for the change in volume. I know the initial volume was 0.5, and I know the change in pressure. So now I can algebraically manipulate this. I can multiply both sides by 0.5, and I can divide both sides by 6.1 times 10 to the 10, and I can solve for what the change in volume of this brass sphere would be under this change in pressure. So hopefully this brings in a new concept of how an object, a solid object, does not necessarily have to remain rigid. But when we're looking at torque, we do assume that those forces that are applied do not cause any sort of stress or strain. We look at sort of ideal conditions. But in terms of realistic, in the real world, like we would have to consider these types of things if we were, going to build something with different materials.